location even with the nearest celestial object and us. So this we have to remember, and this is one of the key points we'll use. So whenever we look at any object, we are looking at how it is in the past. Just to complete, if you take M31, it takes about 110,000 years. Farthest observable galaxy, I think as of today, it is about 14 billion years. So clearly light from these objects are going to take enormous amount of time to travel towards you. Okay, let's also have some numbers for us. A typical lifetime of a star. Okay, a star means like we can think of stars with it having different sizes, different masses. So typically, if you take a value, it can be anywhere between 1 million year to 1 billion years. Okay, so we can now see if a star is at a distance where light travel time is more than 1 billion year. When I see the star today, it might not be present at that location at the instantaneous time. So this is a very interesting point to remember. Yeah, so any question or anything I'm hearing. So please stop me in case I'm not audible or some issues are there. Okay. Similarly, you know that in the sky there are objects known as quasars. So what kind of lifetime they have? So they take about 1 to 100 million years. So just remember these numbers, right? Lifetime of a star can become between 1 million to 1 billion year. A quasar can have a time scale between 1 to 100 million year. Lifetime of transient event, some burst which goes on, can be anywhere between an hour and few days. Okay. If you take collection of stars, we call them as galaxies. So even though individual stars in a galaxy can born and die over a period of million to billion year, galaxy as an entity can remain for few billion years without any problems. Okay, so this just you just understood nearest star, how much time it takes, center of our galaxy, nearest galaxies. Okay, so these numbers are important for us to remember that we are dealing with vast universe, where if you want to do physics, you have to account for the fact that there is a time delay between what we see in an object and what exactly happened in that object. Okay, and if we also keep these numbers in place, we will also understand. If you look at an object, for example, if I look at sun now, I know that sun was there 6-8 minutes back, and it is still there, kind of, right? You can understand that. Okay, because sun's lifetime may be much larger than the delay between us and sun, right? Time delay between us and sun. Okay, that's the point I wanted to keep you in mind. Now, sorry, please go ahead. Yeah, I am changing. Are you not seeing it or what? So if I will play again, can you just tell me whether you are seeing it moving? Okay, so then can I use this and go ahead with this? So now can you see? But the problem is I'll have some things hanging around here. So if I do this, do you see this slides changing? So is it visible enough? The problem is it's not going in full screen mode. It has some problem. If I go ahead with this, is it fine with you guys? I can proceed. Okay, so up to this point, so I was just telling that I was talking about time delay between object and us. Then I was showing this slide where we are talking about time scale of individual objects of our interest. Okay, this is what I mentioned. Then I moved to this slide where I wanted to bring to the fact whatever we are calling at observable universe is nothing but a 2D projection, two-dimensional projection of our world. You can think of as 3D world. So the problem with this 2D projection is that a object that looks faint could be intrinsically bright. It appears faint because it is at a far away distance. Similarly, a compact object which looks extremely compact may be actually a very extended one, but it appears compact because it is very far away from us. Okay, so this is the thing you have to remember. That means if you want to make any First of all, we know that distances and time are related from whatever I was explaining to you. But to get there, it is important for us to figure out which object is near us, which object is far away from us. This is difficult for us to do because of these two degeneracies I have mentioned. The sizes are not standard, brightness are not standard. Okay, this is what we have to do. Of course, our life would have been miserable if that was the situation, but looks like certain things are there in the universe which are helping us. The first thing was something known as cosmic microwave background. What happened was in 1960s, and you can see in the left-hand side, there is a beautiful antenna which is there. And it was originally built to track aircrafts coming from distant. But when people started observing with this antenna, people started detecting signal from every direction. The first thing which happened was the signal was there everywhere. And if you map them very carefully, you find that this is almost like a black body radiation with a temperature of about 2.7 Kelvin coming from all directions. So it looks like is omnipresent. So it is called background, means like this radiation is there everywhere, in every direction, with a uniform precision. In the sense that if I look at one direction and look at some other direction, if I make a measurement of temperature and the temperature were extremely accurate, and today we know that it is accurate at the 5th decimal place, okay, 5th or 6th decimal place, 5th decimal place to be precise. So clearly this is a point. So we know that if some by the way, this is one of the best measured black body radiation in the nature, right? Because this spectrum fits perfectly to the definition of what we call as black body radiation. What is black body radiation? We understand that black body radiation means matter and radiations are in some sort of equilibrium. This is, in crudely speaking, this is a place where existence of E equal to mc square can be proved, in the sense that matter strongly interact with radiation, right? Matter absorbs radiation, emit radiation. This is the interaction which is going on. This interaction is in some sort of equilibrium. So the radiation spectrum and the temperature of the gas to which this radiation is interacting, they can be in equilibrium. So this is the physics, which is nothing to do with, I am not trying to connect anything with what observations we have. Suppose if I want to produce a radiation, which is a thermal black body radiation, what I need is that I need radiation strongly interacting with matter. Okay, this is what we need. So as a physicist, if you find a perfect black body radiation, then you can imagine that in some place in our universe, or this kind of thing possible. Okay, matter and radiations are in strong interactions. That's the first thing we can conclude. That means at some stage the radiation is originating from a physical region which is in some kind of equilibrium. So up to this point, you just I guess that you are getting what I'm trying to say. That's fine. But now comes the problem. So I look at in the north, so I'm looking at completely different hemisphere of the universe. I can go south and look at the universe. I'm looking at some other universe. I'm saying that the same radiation with the same kind of spectrum is present in both directions, which is a problem. What is the problem? That means the sky in the north, or the portion of the sky in the north, should know that how the portion of the sky in the south has behaved in this equilibrium. That means this equilibrium, physics of this equilibrium is known to every bit of our universe. So this is the interesting problem. And we just now discussed that if I want to know what sun is doing, I need to wait for 8 minutes. If I want to know what is happening in the center of my galaxy, I need to wait for 100,000 years. Okay, but we are saying somehow universe, which is kind of infinite in size, knows that what one part of the universe is doing with the other part of the universe. Okay, this is the kind of anomaly we end up with. So how do you solve it? Again, you can come up with a simple theory saying that maybe we have we can imagine the whole universe was causally connected. Causally connected means that the whole region of emission was so small at some point of time, they know exactly what to do. At that time, they were instantaneously connecting with each other. And for some reason, now the radiation was created and the radiation was allowed to freeze like that, right? So only thing you say is that, okay, I know that radiation in the north and radiation in the south are absolutely identical, which means that the creation region should be causally connected. If the creation region has to be causally connected, it has to be extremely small. So you can understand, you can think of as if these radiations were created in a causally connected region and allowed to expand all over the place. So this is the kind of simple physical model one can think of. But it's a model, it's a story, right? You cannot go any further than that. The next observation in the similar year, right, in the same decade happened. This is because of Hubble. What Edwin Hubble found was he looked at the galaxies, different galaxies at different distances, and started doing spectroscopy. When he did the spectroscopy, he found that all the laboratory lines atoms emit in the laboratory, they are also seen in space. That's very interesting. That means like space is filled with gas and gas of different atoms, and they are also excited the way you get them excited in the laboratories, and they emit radiation. Okay, these lines are emitted because electrons go from one energy level to another energy level, and that creates the energy difference is given as radiation. The radiation is coming towards you. But what we all know now is that the radiation, even though the radiations are coming from the atoms, but exact wavelength at which we are measuring them is not identical to what we do in the laboratory. All of them tend to be shifted slightly at the longer wavelength side, which we call it as redshifts. So Hubble measured that all galaxies are redshifting with respect to us, which means in a crude way, it is like moving away from us. Crude way, I'm saying. So he plotted the apparent speed. Apparent speed is nothing but apparent offset of wavelength with respect to laboratory wavelength as a function of distance. Distance he initially calibrated with brightness, but later on, nowadays we do this experiment much more precisely. I will not go into, but I'm just explaining you. When he plotted distance versus speed, then he found that further the objects they are moving away from us at a higher speed. Of course, this moving away is not a good example to take because making an object like galaxy move with high speed is not possible. At the speed at which the wavelengths are shifted, it's not possible. But it becomes very apparent when the same era when microwave background was discovered. Hubble found that there is a possibility that when we look outside, the galaxies move away from us, and further we look, the speed at which they seem to move is larger. Of course, here again you use simple logical principles of physics. First thing is that we always want to be general in our approach. We don't want to say Earth is the center of the universe. Second thing, because we need to assume that if you say that whatever I am seeing, I look around me and whatever I am seeing is special, right? Because they are all moving away from me. But if you say that general physics is valid everywhere, what is the inference you can draw from this observation is that we are one of those points in the universe where when we observe, the objects seem to move away from us. If I shift my point to some other location, if the physics is universal, I should see the same thing in all places, right? So this is the important decision one has to make. We don't want to be very special to start with. So we see that we are one of the observation point and we are not special. If you go to any other point, we should see the same thing. So that means this expansion kind of picture was emerging from there. I will explain in a bit of time. Instead of we being the center of attraction, we say that how we can explain whatever we are observing being happening in any other point in the universe. Okay. So also in a jovial way, we also don't want to be people who are not liked by these galaxies. Why should they move away from us? That means what did we do so that they don't like us? Simple explanation for this come from what we today call as cosmological redshifts. We can understand it in the following way. If you look at the Doppler shift equation, lambda observed will be lambda rest into 1 plus v by c, v being the velocity at which the objects the emitting source moving away from us. Plus is going away in this reference. In the measurements, we can also write it down as lambda naught as lambda r into 1 plus z, where z being lambda naught by lambda r minus 1 is the measurable quantity which you can measure, right? Z being the quantity which you can measure based on what is lambda naught and what is lambda r. So now we can look at what is z. Z is nothing but V by C in this equation. But we can also write down at V by C as 1 by C into dr by dt. So I missed out C there, but you can imagine what I'm saying, right? V by C is nothing but d by dr by dt into 1 by C. So now what is R? This is where the philosophy comes in. R is the distance between 2 points, okay? But if you take R as a vector, R is some scale multiplied by a distance, right? You can think of like this. The distance between me and this thing is measured in some unit. Depending upon what unit I am choosing, the value will be different. Okay, we are going into that way. So if you define R as some scale into distance, my scale can be a meter, and the distance in that scale is what is my distance, okay? So now we can define the redshift as dA by dt into 1 by C, which is the amount by which say these are two ways of doing it. One is that dr by dt can be contributed by changes in length, dl by dt, which is what we usually do in Earth, right? If you want to measure a speed, because our scale is fixed, that's why when we ask for velocity, we just to see how position changes a function of time. On the other hand, we can also think of a situation where distance between two objects have never changed, but the scale which we are using is changing as a function of time. So if you do that, then you find that the velocity, what we are defining, is actually coming from the fact that the scale I am using is changing. So this is what is explained in the balloon experiment. You have a grid in which a sinusoid is placed. Okay, you just blow the balloon, and we are seeing if you just concentrate on the line in your frame, you see that the sinusoidal frequency, or we can think of it as being stretched. The sine curve is stretched. But if I put my eye and look at the sine curve with respect to the grids I have drawn there, then you see that the wavelength has not changed, or whatever you call frequency has not changed, right? Because even though we are stretching both scales and this. So this is the philosophy people understood, and this is the philosophy which has been used in cosmology. The basic idea is that if you want to understand the observations of Hubble, what we are saying is that you look at a distant galaxy, the galaxy light is arriving at us, and when I took the spectrum, I find that the wavelengths are shifted by some amount. How do I understand it? The way you understand is that there is a lot of time passed in between the photon emitted by the source, and it is arriving at you. This time is extremely large. Within this time, the universe has expanded from some small size to a slightly larger size, okay? This is exactly like changing A in the above equation, which means that if I find universe, the shift Z by factor 2, if I say that Z is factor 2, 1, 0.5 and all, what I mean is that I am actually telling the amount by which the universe has expanded from the time the photon was emitted till it was received by me in the Earth. Okay, so this understanding was very important for two reasons, because people beginning to see the value of Z is of the order of 0.5, 0.6, 0.7. 0.7 means in a physical movement or whatever standard Doppler shift model, the galaxy, which has something like 10 to the power 10 stars like sun, moving with the speed which is half the velocity of light, which is impossible, right? If you have done relativity little bit, you know that the mass will go to infinity if you have such objects moving with such speeds. It's impossible first of all to move the object with such a speed. So this explanation that what we are seeing is related to the fact that universe is expanding and the photons are taking finite time, and the expansion amount by which the universe expands can be directly measured from these shifts we see in the wavelengths. These are the conjectures you start with. This, as well as the fact that I told you in these observations, we say that to get the black body radiation, the universe could have been causally connected during this equilibrium period where matter and radiations were strongly interacting. So these two are independently a viable scenario, but if you put them together, they become a solid model. This is what is the Big Bang model. What happens in the Big Bang model? We believe that the universe is expanding from as we go along in timeline, which means that if you go back in time, the universe will be smaller and smaller and smaller and smaller. And you know that when you have matter and skews them smaller and smaller and smaller and smaller region, the density goes up. Because density goes up, energy density goes up. So that is the situation. You can actually imagine that there could be a day when matter, radiation, everything is compressed to a smaller volume. So they could exist in an equilibrium scenario. So this is kind of a picture which we developed to study this. So cosmic microwave background and Hubble expansions, both observations were consistent with an expanding universe. In this case, the redshift indicates the amount by which the universe has expanded between the epoch of photon emission and its detection. Okay, so this part is kind of clear to us. So in this sense, universe was very compact in the past. This explains why isotropy of cosmic microwave background is seen. Okay, so this I wanted to emphasize because even today we have a misconception that Hubble flow means there is a large velocity, galaxies moving with large velocity, which is not true. Actually, galaxies move with some velocity, but whatever shift we are seeing is not connected primarily with the motion of galaxies in the universe. Okay. Based on this, now people have built a big model, which is what is known as a Big Bang model. What is Big Bang model? So now we feel the universe could have started from some initial condition. Of course, that is where our imagination and physical intuitions stop. So I will not go to this philosophical region. What is t equal to 0? Is there a t which is negative? Means like is there a t before t equal to 0? With t equal to 0 being the initial time. But I will start with an observable universe, which is like what we call as the time when the radiation and matter decouple from each other. So you can imagine, I mentioned to you, radiation and matter are constantly interacting with each other. That means it is very difficult to distinguish an object or a photon or anything, right? So the standard model tells you the following: the universe was extremely compact. So you can think of like universe being a soup of all fundamental particles in the beginning, slowly atoms emerging from these fundamental particles. Right? These atoms are closely interacting with radiation field. So there is no concept of what is atom and radiation. But since the universe is expanding, the mean separation between particles become large, and mean separation between radiation and particles become large, which means that the close interaction which has been there in the dense medium will slowly become looser and looser and looser. At some stage, the interaction become extremely loose. So they start decoupling. Matter will no more interact with radiation, and radiation will propagate just like photons going in all directions. This is the situation happens around sometime in when the universe was about 300,000 years, and then what happens is that universe just evolve with continuously expanding. So this would have been a simple scenario up to that point. But the challenges we face now is that our universe is not just a collection of gas particle and radiation, but we know that the universe is filled with galaxies. Galaxies are not just simple objects. It has stars, black holes, gas, what and what not. So that is where this beautiful idea of how to build structures in an expanding universe is an important research theme in the present day cosmology research. So just this figure summarizes the background model in which we believe that there was some initial, whatever we call quantum fluctuation, inflation. I will not go into that. Something creates huge amount of energy. That means the matter was in some soup, which you can think of. If you want to build it like the way we understand individual atoms, we are actually going inside like this. You look at it like atom. If you go further, you look at its nucleus. If you go further than that, you will look at quarks and gluons and other things. If you go even further, then you will start looking at even more fundamental issues related to the unification of gravity, matter, radiation, everything there, right? So this is kind of hypothetical theoretical physics scenario. But if you take such a thing happen, this is what universe has gone through during what we call as hot Big Bang. Okay, this is the scenario we were in. What challenges we have is that looks like universe was extremely homogeneous, because that's why the temperature, whichever direction you look at, you get the same temperature. That means at that time the matter radiation field was strongly interacting, but not much difference was there between one place to another place. This is what very important for us, right? This condition is absolutely important, so that whether I am looking at in the northern hemisphere or southern hemisphere, I should see same kind of radiation. So this uniformity is the initial condition. But when I look at my universe in the present day, and you would have seen based on various observations of SDSS or Sloan Digital Sky Survey, any sky survey, this is the plot which is shown here. You can think of like it's a wedge. You see, you fix your telescope to an angle and just scan in one direction. You fix array and just scan in the declination direction, or fix a declination and just allow the sky to pass through, and you start mapping where the galaxies are. This is the kind of distribution of galaxies you will have. In this side is the depth, and this side is the angular distribution in the sky. And you can clearly see that there are large number of galaxies are there, but their galaxies are not uniformly distributed. They are distributed in some regions very clustered way. In some regions they are like voids. Okay? There are no galaxies in some regions. There are a lot more galaxies than normal in some regions. So this is the challenge. Your cosmic micro background tells you that universe should be extremely smooth and homogeneous at some stage. Present-day galaxy observations are saying that the universe, first of all, matter is condensed into small regions called galaxies. These galaxies are not uniformly distributed. Some regions they are more closely assembled. In some regions they are not there at all. So this is the challenge we wanted to do. And our idea is to see whether we can go back in time and map how matter assembles from completely homogeneous setting into what we call as highly inhomogeneous and completely clustered regime we see. This goes by the name large-scale structure formation in the universe. And this is the kind of problem one wants to do. Actually, it has 2 points to it. One is that you can look at the theoretical aspect of it. You start from some initial conditions and see how you can build in inhomogeneities and grow them. And you have to grow them in an expanding universe. It's a very interesting problem where you will simply use gravitational forces to assemble the structures which you see. But what I will be spending in rest of the time is to see like how one can use observational tool to actually see what is going on. And I'm not going to explain all of them, but I will give you a gist of a basic philosophy behind how one is doing this. Okay, so let's move on. So basically, whatever we are seeing in our universe is what we see, right? What we are inferring is what we see. So I like this picture where a person is searching for something, and some other guy and the police comes and asks him like, "What are you searching for?" He said, "I missed something and I'm looking for it." So did you miss it here? The guy says no. But then why are you looking at it here? He says that only here I have enough light to search. So this is exactly what happens if you start searching or if you start observing the universe with optical telescopes, because we are going to just see what is visible, but there is a bias. This bias is what is known as luminosity bias. So it is not necessary that what you see in light is what is there in space, and you can see whether we can come up with some other techniques where you are also sensitive to things which are not emitting light. This is where these absorption lines become interesting for us. So I'll just briefly go through the spectroscopic aspect of what we call as absorption lines. So this is a standard picture you will see everywhere. So if you take a star or some hot light, you take your telescope and observe, you will get the emission, which is related to how hot the star is, right? You will have a black body radiation coming from the star. Suppose imagine that I have a star and I am looking at the star. In my line of sight, there is a lot of gas blob which is present. Then what happens is that the light coming from the star will go through this gas, and the gas being at lower temperature compared to the temperature of the star, it will produce absorption lines. All the atoms in the gas will produce absorption line, and they will appear in the spectrum of the galaxy. So in addition to intrinsic spectrum of the star, in addition to intrinsic spectrum of the star, you will also see some kind of absorption lines which is embedded on that. On the other hand, for some reason, I look at the blob of gas directly through my telescope. There is nothing behind. Then I will not see this black body radiation, but I will see whatever photons which are being absorbed along this direction will be emitted in all 4 pi steradians. Photon absorption means what? In an atom, electron in a ground state goes to the excited state by observing a photon. That means along the direction of propagation of photon, you lose one photon. But this electron will not stay in the excited state for long, and it will come back. When it comes back, the radiation emitted goes in all directions. This is what is known as diffuse emission. So if I look at the telescope and stare at it, I will detect this same gas blob in the form of emission lines only. Okay, this is what is being shown here. So what I am going to focus on in this particular talk is this way of doing it. So you just look at gas there is an object behind, and look at the object and you see a gas in front, and absorption lines seen in the spectrum of this background, the star, will have all the properties related to this gas. Okay, you can say where the gas is, what kind of composition the gas has, whether the gas has, whether it is moving towards me or moving away from me towards the star. All can be done by looking at the absorption lines. So I will not go into too much detail of how we are going to do with this, but because I want to give a broader brush introduction to absorption line physics, so that's what we are going to do. I have put some simple cartoon for explaining something. This is what is known as space-time diagram. X-axis is the distance, y-axis is the time. So let's imagine that one guy is going to walk from this point to this point. Okay. So typically, what will happen is trajectory in this plot will be something going along this diagonal direction, because as he walks, his time is also evolving. So he will go along this direction. You have to just remember it. The experiment we are going to do is that we are going to plant a tomato plant all along the way at the same time. So we have distributed people. They plant the tree all along the time, and then they are going to typically maintain the condition exactly same. They are going to pour water at the same time, fertilizer, what and whatnot. Okay, so this guy may take about 3 months to walk from here to here. That's the distance we are thinking about. Each of this plant is starting from scratch and becomes bigger and become whatever you call, like kind of start giving a tomato fruit. Okay, that's the situation now. So basically, what happens is that when this guy starts from here, he has seen this tree like this. Imagine that he arrived at this point at this time. So then he would have seen. So he is being told that physical state of all the plants along the way are exactly identical. Okay. So what happens is that he would have seen it growing here. Next time when he reach here, he would have seen this growing here. Next time we reach here, he would have seen this scenario. At last he reached the final destination. He would have seen a full-grown tomato plant. Okay. So now, if you ask, there are two ways of seeing how the plant has evolved, right? There are two ways of understanding it. One is that I stay here and I live with the plant, and I would have seen this evolving like this. Another thing is that I am moving away towards some direction, but I am probing the same kind of plant. And this guy's experience of plant at different locations. If he has a clock and if he measure how much time it has taken, if you ask him to tell a story about how the plant has grown, his story will be identical to the story told by a guy who is sitting in a given place and looking at the single plant evolving. So you understood this philosophy? So now you replace these plants by a galaxy, or you replace this plant by quasar or what and what not. Okay. So you can think of this person as a photon emitted from one object which is far away from us. Okay, that photon is coming towards us. When it is coming towards us at when it reaches different distances, the universe is also expanding. This is analogous to this guy traveling towards his destination. Whenever he reaches to some other destination, the universe has changed. Okay, so he is looking at the universe, how it is changing. He is looking at this plant, how it is changing. Similarly, you can think of photons looking at the universe and seeing how it is changing. Thereby, on its trajectory, the photons can imprint evolution of the universe between the time the photon starts its journey from a distant object and us. Okay, this is the simple philosophy of what we call as cosmology. What is happening is that more the distance, the shift will be higher in the wavelength as the interaction of this moving photon with any object in the sky happens at different distances. The wavelength of interaction will be proportional to how far they are away from us in the universe. Okay, so this is a very simple thing. If you remember this, it will become much more easier for us to follow what is going on here. This is what I wanted to say. You can that I already explained. Maybe I'll skip this and then just see. This is during a travel of photon, what all things can change. This is what I am explaining to you. For example, a star can become completely different. It can start from gas. It can be a star. It can live for some time. It can become a red giant. Then it can start expanding and becoming a planetary nebula and explode into a white dwarf. Okay. On the other hand, if it is slightly more massive, it can become a neutron star or a black hole. But you see that evolution means you could capture a photon could capture a star in any of these scenarios, right? Just to say, if a travel time is of the order of this time, you will be capturing a star at any one of these stages. And similar situation can also be in the case of galaxies. You believe galaxies are nothing but collection of gas particles. These gas particles slowly converted into stars so that it becomes collection of stars. Okay, but we also know galaxies as a black hole. The black hole drives matter outside. Okay, two galaxies can merge with each other. So all sorts of things can happen in between a photon starting from one location and reaching us. Because all these time scales, we said the distance object, it takes billion years for photon to come. All these time scales are of the order of few 100 million years to a billion years. So this is simple physics which we will be employing. This is why I started with light travel time and what we have. Okay. So now let me just come to a few slides where we will go through quasar absorption lines and what are they. So these are the quasar spectra. There is a quasar at the top panel. This is called 3C273. This is the names are like this. So what is 3C273? It's a third Cambridge catalog. This is the survey conducted by Cambridge University. This is the 273rd object in that catalog. Okay, and this is a very famous object. And the standard emission lines are there. And you look at the emission lines, and they are shifted by the amount 1.158. That's why this object is at a redshift 0.158. And you know, like how much universe has expanded. It's very little expansion between the light starting from this object and us. Very little means it's pretty high. Okay. On the bottom, you have another object which is called Q1422 plus 2309. Of course, this is not a catalog from some institute starting with Q. The Q is for quasar. 1422 is the right ascension, 14 hour and 22 minutes. And plus 2309 is the 23 degree and 09 minutes. Okay, this is the location of this object. When this object was observed, the wavelengths were shifted by a huge amount. By 3.62 is the redshift. So you can clearly see that the object producing the spectrum shown in the bottom is at a much farther away distance compared to object which is shown in the top panel. And fact that you have a lot more absorption lines are seen. You can see in the bottom spectrum, you have huge amount of absorption lines, whereas here we don't see that much absorption lines. Wavelengths are, I have to use this plot in a different way, but just follow whatever I am saying. There is a spectrum where you see some kind of light here and an emission line here, nothing much. There are few absorption signatures which are here. But once you put an object at a far away distance, the amount of absorption you see is substantially increased. These are not noise levels. These are all absorption lines. What we understand now is that these are the absorption lines produced by material between this object, which is a quasar, which is at a distance 3.62. And you know that the universe has expanded by that much amount when the object started from that point to us, right? It's like 4.6 times the universe has expanded between that point and us. That we remember. So just to put you in this, I have used one of my colleagues has made this movie. The point here is that here is a quasar. This is our telescope, and the photon is going to travel. This is intergalactic space, and there is a galaxy here, and we are going to see how the whole thing is played out. Okay. Let's see bottom. You can see the photon is moving. This blue circle is the location of the photon, and each place when it interacts with the gas, it produces absorption line. And the whole wavelength is shifting because the time is elapsing. So you have to understand, right? This is to mimic the expansion of the universe. So now this photon is approaching a galaxy. Suddenly galaxy means there are a lot more gas and you will find much stronger absorption. First thing is that you will see much stronger absorption developing once it crosses the gas. You see this. And also in this side, you see a lot of absorption lines. These absorption lines, the original absorption lines, whatever, I'm again replaying this, the original absorption, what you are seeing, these are gas particles related to hydrogen atom. But once you come here in a galaxy, you have created large amount of stars. Stars means what? It's a nuclear reactor. Nuclear reactor is usually what? It's converting hydrogen, helium into heavier elements, carbon, nitrogen, oxygen, magnesium, silicon, cobalt, and whatnot. So this is what has been imprinted when it passed through a galaxy. You not only see large amount of absorption from hydrogen, you're also seeing absorption lines produced by different atoms. So this figure describes two things. One is that there is a lot of absorption signatures spectrum will carry if you look at the distant object. Second thing is that since all the universe is expanding at different rates at different time, absorption line produced by the same atom will not come at the same wavelength. It will come shifted by different amount. The most highly shifted line is originating from a gas absorbing at a large distance from us. The gas which is closer to us will produce a shift which is much smaller. And this, you remember, this photon is analogous to a person who was walking in the field looking at this tomato plant. Similarly, you can think of like this guy is looking at a collection of galaxies. If you know the universe has created large number of galaxies and galaxies are on a statistical sense evolving with similar properties, then as he goes through different time, he is looking at evolved population of galaxies compared to his initial time of the journey. So he can, or photon can actually map whatever is happening along the line of sight in the form of absorption lines. I already described to you the absorption lines can be in the form of hydrogen atom or it can be on the form of with different atomic species which you can see there. So what can you do with it, right? So just to give you an example, just to put you in touch with this thing, the weakest hydrogen absorption detectable. 1 minute, I think just. Okay, so the weakest absorption signatures we can detect, for example, how weak the signatures of absorption one can detect. So this, if you take best vacuums, suppose you take a best vacuum we produce in the laboratory and spread it between us and Mumbai, okay? So suppose if you take whatever best vacuum, so if a photon travel over 1,000 years to produce such an absorption, so basically in intergalactic medium, if you want to see the what kind of distance a photon has to travel so that it can produce the weakest absorption. I'll just explain to you in a bit more detail. What do you mean by weakest absorption? Weakest absorption means we can say that this absorption line is produced by some n number of atoms. Okay, I know what is the weakest absorption I am detecting. Suppose if I want to collect that much amount of atom, how far I have to travel in space? Because the space is very, it's like a vacuum, right? It's one of the perfect vacuum. Okay, so if I want to see like how far I have to travel if I want to produce the absorption locally, what I need is that I need a best vacuum. I take the best vacuum chamber and spread it between here and Pune, and whatever the absorption signature it can produce, we can detect it in space. But in space, how much time the photon will travel in such a thing? But space is much more rarer than the best vacuum you produce. In fact, 7 or 8 orders of magnitude rarer than the best vacuum you produce, because of which the distance over which this gas will be spread is much larger. How larger it is? It is about of the order of photon travel time of about 1,000 years. Okay, that's what, just to give you an idea that we are so sensitive to detecting even absorption produced by the best vacuum. So just wanted to tell you. So now let me move on to, without going into detail, I will go very fast on what we have achieved. There are nice things we can do. Say, for example, one of the things people can do is that I told you hydrogen absorption can be detected in the spectrum of distant quasars. But we know hydrogen has an isotope called deuterium, right? So Deuterium absorption, hydrogen absorption has an isotopic shift of about 83 kilometer per second. If you put them in terms of wavelengths, and this is what it is. If I take this is absorption is by hydrogen. This small absorption you are seeing, it will be produced by the deuterium in the same gas. Okay. So Big Bang predicts the ratio. Big Bang model has a very unique prediction. It can tell you what is the number of deuterium you should have for a given number of hydrogen atoms. Okay, and quasar absorption line allow you to measure it. So you can go and measure deuterium, you can go and measure hydrogen atom. Then this ratio will tell us what is the amount of baryons. Baryons mean hydrogen, helium, and all in the universe you have produced from the Big Bang. So first of all, the fact that deuterium is observed is an interesting proof. Second thing is that if you look at the ratio of deuterium to hydrogen atom, they are very close to the what is being predicted by Big Bang model. So for a given density of matter. So this is kind of one of the, whatever we call, one of the proofs of existence of Big Bang model, or other way of looking at it is that is one of the constraints on what kind of universe we need to have if you believe in the Big Bang model. So I'm going slightly fast here, but the physics is very simple. I can go and measure this at any location in the universe, right? Because if deuterium and hydrogen are created in the Big Bang, like cosmic microwave background, this ratio should remain constant all over the place. Okay, so this can be tested. So this has been tested, and that is one of the important measurements come from looking at quasar spectrum. Of course, I am going to go to the next question, saying that, so if that is the case, if I go sometime back in my in the universe, sometime I go back sometime back, what will I look at? So I should look at this radiation temperature to be higher than what it is today. Today, if it is 2.7, if you go back in time, the radiation should become higher and higher and higher in temperature, right? Because it's getting compressed into smaller volume. And how should it be changing? So this is the curve which is given here. This is redshift. You remember now I don't have to define what is redshift. Redshift is that amount by which the universe has expanded. And this is the temperature. If you plot temperature as a function of redshift, it has to go like 1 plus z. This is what is the prediction. Okay, this is the prediction of this curve is the prediction. So what we are saying, if you look at absorption line happening at with some redshift 3, if I make a conjecture that I am going to sit there and look at the universe around me, what temperature I would have found? I would have found the temperature which is 4 times that of what temperature I am finding today. Okay. So now the question is, can I measure this temperature? So how do I measure this temperature? We know that even human bodies, we measure the temperature using 2 methods. First method is that we put our thermometer. Physics is that you make a matter in thermal equilibrium with your body. That matter expands, and if you have a calibration of expansion of that body in equilibrium as a function of temperature, you can measure the temperature. Okay, can I use the method? So this is what one can do. For example, we said like the radiation and matter were interacting at some stage, and later on, so they all universe become extremely bigger and diluted, so their interactions weakened. But it's also possible that the atoms which are newly created during the process of star formation and ejection, they can have energy levels. The energy levels means ground state to excited state in an atom, which has an energy which is proportional to the actual temperature of the background radiation. If such a situation happens, the radiation start exciting an electron in the ground state to an excited state by just pumping it. Okay, this is what is a conjecture. Suppose you find, is there any energy level in atoms or molecules that can interact with the radiation of temperature 10 Kelvin, 20 Kelvin, 30 Kelvin, 40 Kelvin at different temperature? If you find such an atom, then what will happen is that since these atoms are going to be present in a radiation which is always there, these atoms will have problem in keeping their electrons in the ground state, because whenever they try to keep the electrons in the ground state, this cosmic microwave background will push them to the first excited state. Okay, so the meaning like whatever you call smoking gun discovery will be that if you have such an atom which is present, and this atom can interact with radiation at a particular epoch. If you go and pick up these atoms at that epoch, you will find that electrons cannot be in the ground state all the time. They will try to go up as much as possible because they are embedded in a radiation which is pushing it upwards. My analogy I give in my talk is that you will peacefully live in a ground in a n-story building. You will be happy to be in a ground story. But if you imagine that this is a place where it is very much affected by flood all the time, people will avoid living in the ground floor, right? This is the analogy. So we can look at this way. So this is also a doable experiment. If you pick different atoms at different redshifts, the amount by which they will be shifted will be different also, because the temperature is keep on increasing. So this is a very interesting problem. I give it in a colloquial way, but we managed to find such atoms. For example, neutral carbon has some energy levels which can be in equilibrium with the cosmic microwave background. Carbon monoxide have certain rotational levels which can be in equilibrium with that. So we identify these atoms and we started measuring the excitation, how electrons are distributed in the ground and first excited states, and then you can quantify how much is the radiation which is required to keep them there. These are the measurements which you see as points with error bars, and I'm sure like you agree with me saying that these points are exactly lying on the prediction curve. It's not, the curve is not the fit to the data, curve is the prediction from the Big Bang. So this once again proves that cosmic microwave background is actually evolving like a radiation evolving in an expanding universe. Okay, so this is one of these important discoveries which proves that Big Bang model is not just a conjecture, it has a lot of observables. The next slide, I will just give you what all the things we can do with it. Okay, what are the other things we can progress with absorption line itself? One is that we can also ask this question. For example, we use all the fundamental constants, right? Gravitational constant, electromagnetic coupling constants. There are, whenever you are treating interaction between photon and particle, particle and particle, particle and gravity, we need some constants of proportionality which governs the physical laws. And we believe that this constant of proportionality should not change as a function of time. So the question you can ask is that, for example, can I probe whether these fundamental constants are same in all the galaxies at all the time? Or today it is the value we know. If you go to some other galaxy, the value will change. So this can again be tested through absorption line studies, because again you ask this question, energy level or quantum mechanics tells you what is the frequency over which a certain transition occur will also govern by some of these fundamental constants. So if you can show that lines produced by the same atom coming at the same wavelength, irrespective of whether you are observing in our lab or in our galaxy, or after taking into account all this cosmic expansion and other things, if you can show that fundamentally the resonance frequencies of atoms are exactly identical, you can show that the universe is actually physical laws are governed, the same physical laws are governed all over the universe. Such an exercise, important exercise, is regularly happening, and I'm not going in detail, but you can believe me that we have some intelligent way of defining these projects. And as far as latest results are concerned, we have not found any violations of fundamental physical laws over the past couple of billion years. So this is kind of very, very interesting. So we also know something we realized because of quasar absorption line studies is that we said like universe started from hot Big Bang, then it cooled down, then matter become neutral, and the radiation decoupled from that. We can actually probe how the matter and radiations were behaving as a function of time, and this has led to the scenario where what is known as reionization. So I will leave it. If somebody is interested, I can go through it during these things. This absorption line studies also give important constraints on how galaxies form and evolve. I don't go into this now because I'm already close to an hour. I'll just summarize with a couple of slides, which is I hope I give a flavor of what can be done, and more importantly, what is the philosophy and what kind of approach we are taking to use spectroscopy to draw various physical conclusions. There are two important milestones which will happen because we are involved in two major big telescopes. One is that 30-meter telescope. The idea is that bigger the telescope, you are going to find fainter and fainter objects. It is most likely that these fainter objects are going to come from much further distances. That means your ability to probe the universe over a larger time scale is going to be much better. This telescope project is supposed to be operational 2028. We are facing some difficulty because in Hawaii, people are agitating against using their land to build this telescope, and we hope to solve it at some point of time. Okay. Another project which is happening is what is known as square kilometer array, because this is the largest radio telescope being built in South Africa and in Australia. India is about 6% partner in this project, but this is going to be operational in a couple of years because the project is going well, and the prototypes built to validate the technology is very much in place, and we already have some good results coming out of these prototypes. So I have no doubt that you will start looking at molecular lines and atomic lines and all sorts of lines. Even you can do absorption line spectroscopy in radio, which will give more insights into the problems we are discussing. Lastly, just to give what kind of power we will have, just to stop before this is the last slide, I just wanted to show one thought experiment which we will be able to do so that you can see the power of such big telescopes. So I just told you, when you look at quasar absorption lines, this kind of spectrum is there when the object is far away. Each one of them is the absorption produced by hydrogen. Okay, so imagine that you have a sight line through which photon has propagated. So we thought about one photon which has traveled through the whole universe. Suppose you imagine that after sending the first photon, I send another photon after, say, 10 years. When the photon now comes through the gas, this gas would have moved by little bit amount, right? All of them would have moved by very tiny amount compared to the first photon which has traveled. So my experiment, I'm just changing the same thing we have discussed before. One guy was traveling, and he found how tomato was growing. So imagine that one guy started, and if you send the second guy after 3 days, these two guys will be able to tell you what happened in the gap of 3 days, because that is the thing we can see. For example, if universe is expanding, that means the absorption producing gas is also expanding. In a colloquial way, it is as if the distance between that gas and me is also going to be increasing, right? That means compared to the first set of photons, I cannot say first photon, it's a first set of photons. The second set of photons will see these absorbing gas shifted by small amount, okay? So if you have very high quality spectroscopy, you can go and look at each line and see how much these lines are shifted. Meaning you observe this quasar today, you observe the quasar after 10 years or 15 years. So what you are doing, it's equivalent of collecting a set of particles and today and collecting a set of particles 10 years afterwards. But you are gathering them after they transited through billions of years. But the initial time delay will still remain because they are moving with constant velocity. Okay. So it's the interesting experiment. The experiment is extremely simple. You measure this object today, forget about it for next 10 years. Then go and measure the spectrum again, and you should be able to see the shifts. And what kind of shifts one is predicting, because the cosmology predicts some shifts, and if you see they are all very small. It's like of the order of few tens of centimeters per second if you write down in terms of velocities. These are, if you can go to this is the kind of precision you want to have to detect planets around stars and all, right? So this is achievable with future telescopes. The other way of saying is that if this works out, you are going to see expansion of the universe in your eye directly. Okay. With this, I'll stop. I hope I have given you enough idea that how this science is done, and we are using no light to study the whole universe. That's why it's very interesting for me. I'll stop here, and if there are any questions, I can take. Hello?
Sir, I'm audible?
Yes, please.
Sorry for that. Thank you, sir, for such a wonderful talk. Now is the time for the Q&A sessions. So if there are any questions, please raise your hand, or you can write it on the chat box also.
Can I come out of sharing because that could help? I
Sure, sir.
think.
Yes, Shamprit Dash, please go ahead.
Okay, good evening, sir. And I firstly want to say that the talk was great and I enjoyed it very much. Uh, so means my question is in one video you showed in the presentation about a photon traveling through the universe and the corresponding absorption lines appearing in the spectrum. But initially I saw in the spectrum that there is a means something of a maxima in the spectrum. So what does it signify? That signifies.
So that is, we were mimicking a quasar spectrum. That signifies the emission lines in the quasar. That's what is used to measure the distance of the quasar. So quasars usually have large number of emission lines, right? It's just to show that. I could have plotted without the emission also. That is just to symbolize the light source is a quasar. Yeah.
So means it's a property of the quasar, not because of the traveling of the photon or anything.
No, 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 no.
It's related to the quasar. Okay, sir. Thank you very much, sir.
Any more questions? Please raise your hand or uh, write it on the chat box. Okay, if there are no other questions, we are going to conclude this session. Okay, if there are no other questions, I have also shared a link for the feedback form to let us know your thoughts. And we again thank you so much, sir, for taking all this time and having this wonderful session with us. Thank you everyone for joining. We can conclude this session.
Thank you. Thank you. All the best. Bye.
Thank you, sir.